myself Dr. Pallavi Railavhale. I am going to teach you BP 405T pharmacognosy subject, and we are presently discussing the unit 4, and the topic for discussion is the definition, classification, properties and test for identification of flavonoids. So, first of all, what are these flavonoids? So, flavonoids are basically colored substances which are present in the plants. They are generally of a polyphenolic nature and have a basic ring structure of C6, C3, C6, means two benzene rings. When they are joined together by 3 carbon atom, we have the basic flavonoidal structure. So, they are a group of polyphenolic compounds found in fruits, flowers, seeds and vegetables, and they are generally present in higher plants, for example, Polygonaceae family, Rutaceae family, Leguminosae family, Umbelliferae family and Compositae family. The name flavonoid comes from the Latin word flavus, which means yellow. Okay. So, generally all the flavonoids have a yellowish coloration. So, due to this nature of these flavonoids, the name has been given flavonoids, and it belongs to a plant secondary metabolite category. Now, what is the physiological role of these flavonoids in plants? In plants generally they have a limited role and also have a very low toxicity. Okay, they have a very low toxicity if I compare with alkaloids. However, the pigments in the flowers, they help in attracting the pollinators in the form of insects. They also help in the particular plant in growth control by inhibiting and activating various enzymes. So, they have a very limited role, I would say, in the plants, that is why they are falling in the secondary glycoside category. Now, if you look at the basic structure of the flavonoids, as you can see that it has a basic 15 carbon containing structure, where we have the 2 benzene rings joined together by a linear 3 carbon chain, and the skeleton here represents like this. We have a C6, C3, this is 1, 2 and 3 carbon atom, and then we have again a C6. So, we have C6, C3 and C6 structure representing 15 carbon structure. Okay. Now, the 3 carbons in between which are joining the structure, they vary many times depending upon, there can be extra oxygen which can be added, a phenyl ring can be attached, or any other different type of structure can be formed. Okay. So, here if we look at 2 examples, for example, this structure we have C6, we have C6 here, but if we talk about the 3 carbon atoms, we have 1, 2 and 3. So, it is sufficing the flavonoidal structure, but here we can see that a 5 membered furan ring is present here. Okay. So, in such cases we will call such structure as a orones. They are known as the orones, and they are generally rare structure. The orones are rare structures. The second category are the flavonoids, which are having a 6 membered pyran ring. As you can see this is a 6 membered pyran ring. The structure remains the same. We have C6, C6 and here we have 1, 2 and 3 carbon atom. But here rather than having a 5 membered ring, we are having a 6 membered pyran ring, making it as a flavonoidal structure. Now, in this flavonoidal structure only, if we classify these flavonoids based on the different functional groups present in the structure, then they are named as shown. First of all, the flavones. So, flavones are nothing but, this is our C6, the second C6 group which is present, this is C6, the second C6 group, and here you have 1, 2 and 3 carbon atoms. So, at the 4th position, when we have the presence of a keto moiety, it means it is 2-phenyl chromine 4-one. Okay, we at the 4th position we are having the keto group. So, it is known as a flavone. It is known as a flavone. ONE stands for the ketone present. Okay, and the name is The example for this flavones are apigenin, luteolin, tenegritin, etc. The next category is similar, where we have the keto group at the 4th position, but at the 3rd position we also have a hydroxy group. Okay. So, now the name becomes, it is 3-hydroxy 2-phenylchromine 4-one. So, it is having ONE also, and it is having the hydroxy, giving it the structure. ON stands for the ketone and OL stands for the alcohol. So, it becomes flavonol. Okay. Now, it is flavonol. Example for flavonol is rutin, quercetin and kaempferol. Next category is that of flavonone. So, in flavonone we have 2,3-dihydro-4-chromine 4-one. So, what is happening here? That in the last two structures there was a double bond. Just check here, if you can see that there was a double bond which was present at the 2nd and the 3rd position in both the structures. But now this double bond is missing, it is not present. So, the structure is the same as flavone, but now it is known as flavonone. Okay. It is 2,3-dihydro 2-phenylchromine 4-one, and the example is hesperetin and naringin. Now, the 4th example, what happens is same way like we had the flavonol. Here, because we have the keto group, and the hydroxy group at the 4th and 3rd position respectively, because of which it becomes 4-flavonol. Okay. Now, it is, just see, it is flavanonol. So, OL is there, but now it has become a flavan, just like here. Okay. So, examples for this is taxifolene, silymarin, and the IUPAC name is 3-hydroxy 2,3-dihydro 2-phenylchromine 4-one. Then further we can categorize as flavans. So, in flavans what happens, that there is a C6 and C6 moiety present on both the sides, and here at the 2nd, 3rd and 4th moiety you do not have as such any present. In that case it is known as a flavan. Now, in case at the 3rd position there is a hydroxy group, we will call it as a flavan 3-ol, and in case if there is a I will just erase it, and in case at the 4th position if we have a hydroxy group, then it is known as flavan 4-ol. And there can be a situation where we can have hydroxy group at both the 3rd and the 4th position, then we will call it as flavan 3,4-diol. So, all are these various examples of flavonoids only. Now, after we move further the flavonoid, there is a similar category which is also effectively very good antioxidants, and many of the activities have been determined lately. For example, their antibacterial effects, antifungal effects, anti-tumor effects as well as anti-inflammatory properties. And the basic structure here is, it has a C6 structure, again it is having 3 carbon atoms, but there is no ring structure which is present. So, we can say chalcone is a type of a flavonoid. It is also slightly yellowish or creamish in nature. Then we come to the chemical test of flavonoids. So, generally as discussed in the last class, the first test is the Shinoda test. For Shinoda test, we will take the dry powder or the extract, and to that we will add 5 ml of 95% ethanol and few drops of concentrated hydrochloric acid, followed by magnesium turnings. So, a pink color is observed. In case this is not very clear, we can replace the magnesium turnings with zinc turnings, and that is the modified Shinoda test. Now, another test is there when we can take the small quantity of the drug and add lead acetate solution. So, a yellow colored precipitate is formed. Now, addition of increasing amount of sodium hydroxide to this residue shows yellow coloration. which decolorizes after addition of any acid. Now, in this chapter itself we have another topic of resins. So, we will be continuing with the resins also on the same lines as flavonoids. Resin can be defined as a complex amorphous product of more or less solid characteristics, which on heating first sets soften and then melts and are chemical mixture of volatile oils, oxygenated products of volatile oils and carboxylic acids. So, resins are generally they are synthesized from the precursors which are nothing but the volatile oils. Okay. So, like if a tree it is having any kind of injury or any kind of infection, in such cases what happens that the volatile oil present in those plants, they start converting automatically to its byproducts in the form of resins. Generally they are used as an excretory material of the plant, but these resins due to their aroma and their properties, they are generally used as in the formulation of many of the drugs, either as a pharmaceutical aid or a drug itself. Okay. The best example of a resin I can give is hing or asafoetida, which is having a very good carminative effect. So, resins are produced and stored in the plants in the schizogenous or schizolysogenous glands or cavities of the plants, just like the volatile oils. And you have to remember that they are generally the amorphous substances, and if we have to determine them chemically, they are very difficult to determine because they exist as a complex structure. And generally how is the complex made? It is a mixture of the volatile oils, their oxygenated products or the intermediates, as well as their final products, which are nothing but the carboxylic acid. So, this reaction it is going on continuously, and therefore, we will always get a complex mixture and not individual ingredients. So, these are the few pictures depicting how from the tree they are just when there is any kind of injury made or cut made, they start releasing from the plant in the form of droplets, and when they are collected they solidify into a you can say a slightly soft mass, which on heating starts melting. These are few more examples as you can see. Now, this picture here it is a insect which uses the plant substances also, processes it through its body, and then it starts releasing or secreting this constituent known as shellac or lac. It is also known as lac. This is also a type of resinous material. The properties of these resins, generally isolated resin products which come as an unorganized crude drugs in market are more or less solid, hard, transparent or translucent materials. Resins are insoluble in most polar and non-polar solvents like water and petroleum ether respectively, but they dissolve completely in alcohol, solvent ether, benzene or chloroform. The chemical compositions, it can be a complex mixture of alcohols, acids, phenols, esters, glycosides or hydrocarbons, and they are generally composed of monoterpenoids, sesquiterpenoids or diterpenoids of the volatile oils. The gums which are associated with resins are similar to acacia gum, which sometimes possess similar qualities of the oxidase enzyme. So, here I would like to add that for example, in the plants we have cellulose also, and when there is any injury in the cellulose, the bacteria act on this cellulose and convert this cellulose into gums. Okay. Same way volatile oil are getting converted into resins. So, what happens many times these gums and resins combine together to form the gum resins. So, as the name suggests, like acacia is a type of gum. So, in the same form when a resin it is combining with any kind of gum, we call it a resin combination. In that case what will we call it? Resin combination. Resin can be of the physiological origin such as the secretion of the ducts. They can also be pathological products, means the plant can automatically release the resins, or sometimes we have to do an injury and because of the pathogens, means the bacterial attack, only then the production of the products takes place. Then in that case we will call it a pathological product. Here the example I would like to give is that if I talk about Hing or Asafoetida. So, in case of Asafoetida, we have to make injury in the roots of the Asafoetida plant. After that only it starts releasing the Hing, okay, the resin. But if we take the example of Mir, Mir is a tree and on its bark automatically the tears of the tree come out in the form of the Mir resin. Okay. So, it is a physiological resin, no injury is made for production of resin in the Mir plant. Now, the classification of this Mir, basically of these resins, they are generally based, they are classified based on their chemical nature, and secondly on their association with the other group of compounds like either the oils or the gums. If we talk about those classification based on the functional groups, then they are classified as resin acids, resin esters, resin alcohols and resin phenols. In resin acids, we have the carboxylic acids which contain resinous substances which may or may not have association with the phenolic compounds. These compounds are found in free states or as the ester derivatives. Abatic acid and chromophoric acid that are present in colophony and myrrh are examples of the resinous acid. So, you can see the picture of colophony here, which is a resinous acid. Resinous esters. Resinous esters are the esters of resin acids or other aromatic compounds like benzoic acid, cinnamic acid or salicylic acid, and they are sometimes converted to their free acids by the treatment with caustic alkalis like NaOH or potassium hydroxide. So, this is the structure of benzoin which is produced from different plants. Then we have the resin alcohols, they are also known as resinols and they are complex alcoholic compounds of high molecular weights. They are found as either free alcohols or as esters of benzoic, salicylic acid and cinnamic acids. They are insoluble in aqueous alkali solution, but soluble in alcohol and ether. Resinols are present in benzoin also as benzoresinol and in storax as storcinol. Okay. They are also present as storcinol in case of storax. And the example is balsam of Peru which contains some quantities of the resinols as well. Resin phenols. So, here we have the phenolic structure in the resins also known as resinotanols and they have high molecular weight compounds which occur either in free states or as esters. Due to its phenolic nature, they form the phenoxoids and become soluble in aqueous alkali solutions. However, they are insoluble in water and dissolve in alcohol and ether. And the example is the cashew nut liquid. So, the liquid produced from the kaju or cashew nuts that contains this resin phenols. Further, they can be classified based on the combination. So, if it is existing in the combination with glucose or sugars, then we call it as a glucoresin. If it occurs with oil, we call it oleoresin. If it coils with oil as well as gum, then we call it oleogum resin or it can be gum oleo resin also. If it occurs in combination with glucose and oil, we can call it gluco-oleoresins. Then there are balsams and resins which are complex resinous structures. So, glucoresins, the example is jalap. It is combined with sugars by glycosylation and produce glycoresins. Glycoresins can be hydrolyzed by acidic hydrolysis to the glycone and a glycone. Oleoresins are the homogeneous mixture of resin with volatile oils and the oleoresin possess an essence due to the volatile oils. Turpentine, ginger, copoiba, Canada resin are few important examples of oleoresins. Gum resins are the naturally occurring mixture of resins with gums due to the solubility in water. Gums can be easily separated out from resin by dissolving the gum in water. Ammoniacum is an example of the natural gum resin. Example, here one more example which we have shown is myrrh. Then we have the oleogum resins. Oleogum resins are the naturally occurring resins which are a mixture of resin, volatile oil and gum. The example includes gum, myrrh, asafoetida and gumboj. Then we come to balsams. So, what are these balsams? Balsams, they are generally a complex material which are naturally occurring resinous mixture, and they contain a high amount of the aromatic balsamic acids. So, what are these balsamic acids? They are combination of benzoic acid, cinnamic acid and their esters. So, like benzyl benzoate, cinnamyl cinnamate, benzyl cinnamate, cinnamyl benzoate. So, in this kind of combinations of benzoic acid and cinnamic acid, when we have the presence of a complex structure, in that case we call it as a balsam or the balsamic acids. They have a very good aroma to it, and a very, you can say it's the aroma is very nice, because of which it is used in many of the perfumeries, in many of the pharmaceutical products. Balsams contain free acids and they are partially soluble in hot water. Some important balsams containing drugs are the balsam of Peru, balsam of Tolu, then benzoin and storax. They are generally used as expectorant pharmacologically, and other than that they have the role as a flavoring agent or in a perfumery generally. Then the resins. Resins are chemically inert resinous products and they are generally termed as resins. They are insoluble in water. It is present in asafoetida. So, asafoetida, though it is a complex type of resin, it contains one ingredient which is known as asaresin B. So, this asaresin B, it is present in 50% in our resin, in our asafoetida, and it is a very complex structure. The another example is damar. As you can see, this is a whitish colored compound resin which is obtained from plants. This is also a type of a resinous material. Now, we look at the chemical test of resins. As such, if we search, we do not find general presence of tests for the resins. However, individually there are many tests for different types of resins. Here we have enlisted a few tests for your reference. The first test is the HCl test, where we will use HCl and it leads to the formation of a pink color. Okay. So, if there is a presence of a pink color, then we will say that the test is positive. The second test is the FeCl3 test, where we add FeCl3, it gives a greenish blue color and this shows the presence of the resins. Then we go to the specific test. So, specific test, here we have the amblyopherone test, which is generally done for the asafoetida only. So, this amblyopherone test, we will take HCl and then we will add the concentrated ammonium hydroxide to it. What are we adding? Concentrated ammonium hydroxide. So, it leads to the presence of blue fluorescence, showing the presence of amblyopherone. Okay. So, this amblyopherone, it is found generally in asafoetida only. So, if it is present, means asafoetida is the original asafoetida, because lot of adulteration takes place for this asafoetida. Then we have the copper acetate test, where we add petroleum ether as well as copper acetate to our sample, and it gives the formation of emerald green color, showing the presence of abatic acid. Okay. Abatic acid is found again in different types of the resins, and the one example which I can share is shellac. Okay. Shellac is a rich source of abatic acid. So, we can add copper acetate solution and petroleum ether to it, producing a emerald green color. Okay. So, here we have discussed about the flavonoids. In flavonoids, we discussed about the definition of flavonoids, that it has a 15 carbon containing structure made up of the structure C6, C3, C6. Now, it has yellow coloration, because of which the name flavonoid is given, and in this, if the central 3 carbon atoms, if they form a 5-membered structure of furan ring, we call it a orone. If they form a 6-membered structure of pyran ring, then we call it a flavone. And depending upon the keto groups, the alcoholic groups present in that, they can be classified into different types of flavonoids. The main chemical test for flavonoids is Shinoda test as well as lead acetate test. Then if we look at the resins, resin are complex structures which are a combination of volatile oils, oxygenated products of volatile oils and carboxylic acids, and they generally are, because they are derivatives of volatile oil, they have the properties related to volatile oil. They can be classified based either on their functional groups or on the combinations in which they exist. For example, resin esters, resin alcohols, resin phenols and resin acids. Then if we talk about the combinations, we have gum resins, oleoresins, oleogum resins, then we have the glycoresins, as well as we have the resins and the balsams as the complex resinous structures. And after that, the chemical test we have discussed at the HCl test as well as the FeCl3 test. So, with this we end this class, and in the next class we will be discussing about the next phytochemical category. Thank you very much.